Hey everybody, it's Dr. J, and today, yes, today we're talking about heat and work. Let's talk chemistry. So everybody, we need to understand that energy can be exchanged between our system and surroundings, right? And we can do this through heat and work. So when we're talking about heat and work, heat is what we are going to call basically, we're going to transfer our energy between our objects at different temperatures, right? We've all been exposed to heat before. And we use temperature, right, for this. So in this case, remember, in this case, temperature is the kinetic energy of our particles in a random motion, right? So depending on how fast those particles are moving, that's going to impact your temperature, everybody. Work. Work is basically the force acting through a distance. Okay, so basically, we understand that we're applying a certain force over a certain area. Now, we can actually find work by using this equation here: force times distance, right? Force acting over that distance. And that's how we're able to actually get work. Now, how does heat and work combine to form energy? Well, essentially, energy is equal to our heat and our work, right? That's how we defined energy earlier, right? The ability, the capacity to do work, right? That's essentially what energy is. So depending on how our heat and work are interacting with each other, that's going to impact the change in our energy. Y'all remember that delta E? That's the change in energy. So if we look, right, I got a couple different instances here, situations to where let's look at our Q or our heat. So our heat, basically, if you got a positive Q, right, that means that our system will be gaining energy. So we mentioned this before in our previous videos, but if your chemical reaction, our system is gaining energy, that's an endothermic reaction. If your Q in this case is losing energy, that's going to be what? An exothermic reaction. If you guys forgot about that, look at that. Look at those previous videos, right? So depending on what type of reaction you have, that's going to impact your Q, right? The transfer of energy. Your W is your work, and if your work is being done on a system, okay, so the work's being done on that chemical reaction, that means that you're going to have a positive work. If your work is being done by the system, so if your chemical reaction is doing all the work, right, that means that you're going to have a negative work, all right? So, depending on how these two are interacting with each other, that's going to impact your change in internal energy. So remember, if you have a positive internal energy, that means that energy will be flowing into the system, your chemical reaction. If you have a negative energy, that means that it's flowing out of the system. Okay. Now, one thing that you must consider when we're talking about heat and work are not state functions. Therefore, we're going to care about the process with these two here. Energy, right, this internal energy is a state function. So we only care about the final and initial conditions. So we look at this quick little graph here. I got a pool table, right? We got a smooth table, nice and smooth, and then we got a rough table, nice and rugged. Okay. So let's look at this first example here, the smooth table. All right. We all understand with pool, you got the ball, you hit it with the stick, and then it moves on. Bam, shoot. That's what we do. Okay. So the initial kinetic energy, we're going to say is 5 joules. Okay, so the initial kinetic energy is 5 joules. And when we're talking about the initial kinetic energy, we're talking about when you first hit that ball with the stick, right? When you first hit it, bam, that's how much energy we gave to this ball here at 5 joules. That's how much energy it's going to have. And what we're going to see, right, is that as the ball goes through on that table, right, because it's traveling and then it has to travel over a distance, it will lose some energy. And that energy will be lost as in heat, right? Because it has to travel, it's traveling over this table. Now, once it hits this other ball, right? In this case, a collision is going to occur. Now, the transfer of energy, right? That's all what we talking about with this thermochemistry stuff. So we're going to transfer the energy from when I hit that ball, my first one, right? Then it's going to hit this purple ball. Okay, so what happens to the purple ball? The purple ball is going to travel as well. But notice, right, once it gets hit with this other ball, notice that the energy level is at 4.5 joules. Now, why is it at 4.5 joules? What actually happened here? Right? How do we go from 5 to 4.5? Because of this energy that was lost, right? The heat. We lost this energy over time because it had to travel over a certain distance. Now, what we see here, right? Now, if we look at our purple ball, is that what happens to this energy, right, from our silver ball? Well, now our kinetic energy after our collision is going to be zero, right? It's all of our energy has been transferred from the collision, right? It went from here to the purple ball, all right? So it's all lost. But what we need to understand, right? What we need to understand is that if we look at our internal energy for this instance, we had our work, right? Work that was being done is now at a negative value, and our heat, our Q, was lost. So it went to a 0.5. But in total, right? This is what we understand. That energy level is now a negative 5 joules, right? So we started off with 5 joules, and that energy that was transferred is still going to be 5 joules. That's the key thing we want to understand, everybody, right? The transfer of energy. That 5 joules did not disappear. It just transferred to, right? In this case, to this ball. Some of it went to the ball, and then some of it went to the heat that was lost. But it all went somewhere, right? It didn't just disappear. Okay, so that's what we want. That's what we want to try to understand here, guys. That law of conservation of energy and mass, right? We're not just energy isn't just disappearing out of nowhere, right? It's transferring. It's transferring, right? Energy is constant. Energy cannot be created nor destroyed. Let's look at this last example here, the rough table. So same concept. We initially hit the ball, it's at 5 joules, but notice this time, because it's on a rougher table, we're losing more heat because it's having to travel over a more distance. It's harder to travel. So in this case, we're going to lose 3 joules instead of 0.5. Now that we lost this 3 joules, at that impact, right, our kinetic energy at the collision is going to be 2 joules. Okay. So after, right, the kinetic energy for this ball hits 0, and then as this ball, what do we notice? It's not going to travel as far, right, because it got hit with less energy because it had to do all this traveling on this rougher table. But the key thing we need to understand, even though, right, in both these instances, this one a little bit farther, this one went a lot shorter, okay? But the reason being, right, is we understand the rough and smooth table. We could figure that out. But we need to understand one thing. It's still the same amount of energy for both of these tables. Even though the distances are different, we're still using the same energy for both smooth and rough tables, right? Because at the end of the day, what happened here, right? We lost 3 joules of heat, right, of that energy over the rough table. And that collision, it collided, it gave away those 2 joules. But we need to understand, in total, we started off with 5 joules, and we still transferred those 5 joules. So just because it went a shorter distance, it didn't have any less energy or any more energy or anything like that. It's the same energy at the end of the day, everybody.